A city block, 4 streets wide and 3 streets tall. You are at the bottom left corner. You want the top right, and you refuse to waste a step. How many shortest routes are there? You could trace them out. There are exactly 35. We counted everyone by machine, and you will see all 35 reasons in a moment. Grid sizes and step counts here are non-negative integers, nothing more. A fair question. A classroom question even. But here is the promise of this episode. Before it ends, this same little grid will prove an identity that looks out of reach of any picture. Take any row of Pascal's triangle, square every entry, add them up, and the total is always a single central binomial number. For row 3, 1 plus 9 plus 9 plus 1 is 20. No accident. A grid knows why. Here is the whole idea of this episode, in 2 short sentences. First, a path is not a picture. It is a word, 1 letter R for every step right, 1 letter U for every step up. Counting routes is counting words. Second, and this is the engine, count the same collection of paths from 2 different viewpoints, and the 2 answers must agree because they answer the same question. That agreement is an equation, an identity proved with no algebra at all. Whatever you count, count it twice. First, the correspondence. A shortest route on the 4 by 3 grid takes exactly 4 steps right and 3 steps up, 7 steps, in some order. Read the steps as letters, and the route becomes a 7-letter word. R-R-U-R-U-U-R, say. And it works in reverse. Any arrangement of 4 R's and 3 U's traces a legal route. The match is perfect. 1 route, 1 word, 1 word, 1 route. So the count is the number of ways to choose, which 3 of the 7 positions hold a U. 7 choose 3, 35. The bijection did the counting. The original classroom version of this puzzle uses a 6 by 4 grid. 10 letters, 4 U's, 210 roots, same argument. There is a second, humbler way to count, from the bottom left corner by corner. Every corner can only be entered from its left or from below. So the number of roots to a corner is the number to its left neighbor, plus the number to the one beneath. Fill the grid, ones along the 2 edges, then each entry the sum of 2. 1, 2, 3, 3, 6, 10. These numbers are old friends. Tilt your head. The grid is Pascal's triangle, drawn on street corners. And now notice what we already have. The fill says the corner count is a Pascal entry. The word said it is 7 choose 3. 2 viewpoints, 1 count, and they agree as they must. You have just watched the method work for the first time. Let us say the rule out loud, because it is the key the whole episode turns on. If one family of objects is counted correctly in 2 different ways, the 2 expressions are equal. Not approximately, identically, for every size of the problem. The craft is in choosing the second viewpoint. Slice the family by a different feature, where a path crosses a line, what its first letter is, how many long steps it takes, and each slicing writes the same total in a new notation. Counting once gives a number. Counting twice gives a theorem. Now let the rule run. First, a puzzle about turning. Same 4 by 3 grid. Among the 35 routes, how many turn an odd number of times? Counting turns sounds miserable. So do not count turns, translate them. A route is blocks of R's, alternating with blocks of U's. Each turn is a boundary between blocks. Start with R and end with U. and the blocks alternate R, U, an even number of blocks, hence an odd number of boundaries. Odd turns start and end with the same letter, and the turns come out even. So, odd number of turns, exactly when the first and last steps differ. Now the count is easy. First step R, last step U. The middle is a free root on a smaller grid 10 ways. First U, last R, 10 more. 20 roots. And the machine, checking all 35 words one by one, finds exactly 20 with an odd number of turns. The original version asks this on an 8 by 6 grid. The same translation gives 1584, a numeration again agreeing. Second, add shortcuts, and watch a new species of number appear. Give every block a diagonal shortcut, corner to corner, pointing up and right. Roots may now step right, up, or diagonally. How many roots cross an n by n grid? Direct listing dies fast, but the corner by corner fill survives beautifully. A corner is now entered from the left, from below, or along a diagonal, 3 neighbors instead of 2. Each entry is the sum of 3. 113, 13, 13, then 63. These are the Delana numbers. 3, 13, 63 ways for 1, 2, 3 blocks square. We listed all 13 roots of the 2 by 2 case by machine, 13, as the fill promised. When the sizes grow, sum along the diagonals of the table and a pattern appears. 1, 2, 5, 12, 29. Each number twice the previous plus the one before that. That recurrence is the trade's other key. When direct counting gets heavy, find how the answer feeds on smaller answers. The source material rides it to a sum over a 15-step diagonal, 235,415, and direct machine summation agrees exactly. Third, the promised identity, and the checkpoint that proves it. Take the n by n grid. Count 1, the word argument. 2 n letters, n of them use 2 and choose n roots. For n equals 3, 6 choose 3, 20. Count 2, draw a checkpoint, the anti-diagonal line of corners running from top left to bottom right. Every root must pass through exactly 1 checkpoint corner. No root can touch 2. After crossing, there is no way back. So sort the roots by their checkpoint. To reach checkpoint number k takes k u's among n steps, n choose k ways. To finish from there is the mirror image, n choose k ways again. A square. Sum over the checkpoints. The roots total the sum of n choose k squared. 2 counts, 1 family. So for every n, the squares of row n of Pascal's triangle sum to 2 n choose n. For n equals 3, 1 plus 9 plus 9 plus 1, 20. The promise from the opening kept. A picture proved it. And identities breed identities. The full row of Pascal's triangle sums to 2 to the n. Square that sum, 4 to the n. Expanding the square splits it into the diagonal terms, our sum of squares plus twice the cross products. So the sum of all products n choose I times n choose j over pairs I less than j is 4 to the n minus 2 n choose n, all over 2. For n equals 3, 64 minus 20 halved 22. The machine agrees. No new counting was needed. The checkpoint identity paid a dividend. Last, a different landscape. A strip of triangles, point up, point down, point up, glued in a row. Walk from the left corner to the right, moving only rightward, flat right along an edge, or slanting upright or down right. Fill in the counts corner by corner. 1, 1, 2, 3, 5, 8, 13. Fibonacci, walking across a strip of triangles. Y, a slanted step advances you half a triangle's width. A flat step advances a whole one. So a root is a word of ones and twos adding to the strip's length, and such words obey the Fibonacci recursion. End with a 1 or end with a 2. Now count the strip 2 more ways and collect the dividends. Cut an odd strip at its line of symmetry through the apex of the middle triangle. A root either passes through that apex. Count the halves, multiply a perfect square, or it slips underneath, which splits it into 2 roots on strips 1 size smaller. Another square. So the whole count is a sum of 2 squares. In small numbers, 13 equals 9 plus 4. In Fibonacci language, a Fibonacci number of odd index is the sum of 2 consecutive Fibonacci squares. And the word count, ones and twos, sorted by how many twos, reads the same total off Pascal's triangle along a shallow diagonal. 1 plus 5 plus 6 plus 1, 13 again. 3 viewpoints, 1 strip, 2 classical identities, and not 1 line of induction. How far does counting twice reach? Beyond paths, far beyond. Choose a committee and its chair in 2 orders, and you prove k times n choose k equals n times n minus 1 choose k minus 1. An identity from an earlier episode of this series, now unmasked as the same move. The source material offers more trails we left unwalked, paths that may wander but never descend, counted by choosing 1 gate per story. The craft always is the second viewpoint, a checkpoint line, a symmetry cut, a translation of steps into letters. Nothing here needed induction, and nothing needed algebraic manipulation. The objects themselves carried the proof. When a sum of products looks unprovable, ask what it might be counting, then count that thing another way. 1 episode, 1 move, worn 4 ways. Translate. A path is a word, and words are easy to count. Recurse. When listing gets heavy, let each corner feed on its neighbors. Slice. A checkpoint line turns 1 count into a sum of squares. Cut. A line of symmetry turns Fibonacci into sums of squares. Whenever 2 honest counts meet, an identity is born. Whatever you count, count it twice. "35 roads, every one of them a word.